record button for me?
We are, yep, we're recording.
Okay. Hey, welcome everybody to the first and hopefully only ever Rise Above conference. Personally, I never want to do this online again. You guys can feel free to tell me otherwise at the end of this, but I am happy to introduce our first set of presenters tonight. Ms. Zula Coley, Jay Wheeler, Randy Huerta, John Cole, and Sarah Robinson. Their mentor for this project was Dr. Landon Holbrook, who I hope is on the call today with us. And I am going to turn it over to them and let them talk to you about their project on the irrigation pump sustainability in Turkana. Zula, for you and your group, I will give you a 2-minute warning when you hit 15 minutes. For those of you on the call, please make sure in the chat you submit any questions for the group to me, Kristen Mudrack, so that I can ask at the end of their presentation. Zula and company, the floor is all yours.
Thank you all for joining us today as we present the Turkana irrigation project. Before we begin, I'd like to thank Gene Morden, David Giles, Kip Lines for taking time to work with us. They're a part of CMF International, and they've given us the opportunity to be part of this great work that we've been involved in. So to start, I'd like to introduce CMF International and give some background on how this project came to be. CMF International is a global mission team at work in 25 countries. They're creating Christ-centered communities. CMF International's projects are wide-ranging and multidisciplinary. Because of this, it allowed us to implement our engineering studies to help a community in Kenya. Their mission in Turkana, Kenya centers around spreading the gospel by aiding the community in their efforts to maintain a sustainable garden in a region with very little rainfall. At each irrigation site, local families and churches grow vegetables and fruits like mango, papayas, and kale, etc., to provide for their families. The community garden has had a tremendous impact on the people of the community. In our partnership with CMF International, the goal of our team is to improve the sustainability of their Turkana water and farm development project. This goal entails identifying sustainability problems with their current irrigation equipment, proposing a solution, testing the possible solution, and ultimately providing a report to CMF International with data and recommendations. Their current irrigation system consists of solar panels that power a direct current submersible pump. Gene Morden, CMF International member, brought to our attention that the current system has room for improvement. To start, the current pump used in all Turkana wells costs approximately $2,200 each, which is very expensive in comparison to other pumping options. Also, the current pump is not repairable. Repair parts are not manufactured for the model. Finally, because of the operating conditions, the intermittent supply of power, and the continuous run times, the pumps in the system have been experiencing a shortened lifespan. It has been documented that approximately 12 pumps out of 100 have experienced a lifespan of less than 10 years. Therefore, our project focuses around providing a pump recommendation that is sustainable, repairable, and financially viable. For this project, we determined that an alternating current pump is a more affordable option. We found 2 alternating current pumps that could possibly fit the needs of the community, be less expensive at approximately $300 and $500, and perform in their specific irrigation system. The 2 pumps were purchased and tested. The following test criteria were considered in providing a recommendation for CMF International.
In order to determine the pump selection, we first needed to have a full understanding of the current system. The system as installed by CMF contains a solar panel section to provide power for the pump. This usually contains 2 solar panels. The panels are mounted on a stand that allows them to pivot. They're manually adjusted by members of the community throughout the day so that they can track the sun. The amount of power provided varies with the sunlight throughout the day. One thing CMF mentioned to us is they choose not to utilize a battery storage system for reasons mainly because the cost upfront is significant and it does add some complexity to the system. There is also no power switch on the solar panels, which means that they provide power continuously to the pump as they receive sunlight. This was one area of concern as it shows the pump receiving continuous low power prior to startup in the hours just after sunrise, and then as the sun's going down, again, it's the low power situation. The pump is contained in a 4-inch well casing. The well depth can vary based on location, but usually it will range from 30 to 50 feet deep. The pump is submerged in the well and provides approximately 10 gallons of water per minute to the farms by pumping through a 1 1/4 inch water line. The water lines from the pump to the crop also vary in length. We were informed by CMF contact that the longest length installed was approximately 700 feet. This water is then pumped directly onto the crops. The workers at the crops can allow the water to fill a specific area, and then they're able to just manually move those water lines to ensure sufficient irrigation to different areas of the crop. For proper measurement data, it required us to assemble a testing rig that would allow us to simulate the characteristics of the current system in operation. A power supply would be utilized in place of the solar panels. This would allow the power provided to the pump to be varied, similar to the power that would be provided by the solar panels as the sun changes position during the day. Additionally, due to the selection of alternating current pumps rather than the DC pumps that they had previously used, inverters were added to the system that would allow the conversion of DC power provided from the solar panels to AC powered, which was required for the pumps. The well casing was modeled using a 4-inch PVC pipe that the pump could be submerged in. This also required a 55-gallon plastic barrel to be used as a water reservoir to ensure the pump had sufficient flow and would not run out of water. The pump outlet contains a pressure gauge followed by a valve. The valve can be manually adjusted until a desired pressure value was met on the pressure gauge. This allows a simulation of the pressure lost from the system. The parameters such as well depth and pipe length would affect that pressure loss. After the valve, there is a flow meter that allows us to verify the flow after the pressure losses to ensure that the flow is capable of meeting the 10-gallon per minute requirement that the current irrigation system was producing. This data could be logged on devices located in the electric box, which is attached towards the front of the testing rig. By utilization of this data logging, it allows the parameters to be monitored for a given time to determine that steady state has been reached, and the data could be viewed as reliable.
Next is the engineering analysis. There was multiple things we had to do for that. The first one, this is more for the mechanical side of the project, was the head calculator. The head calculator represents the pressure loss through the system. The head calculator is an Excel calculator that was built to allow the system parameters mentioned previously, such as well depth and pipe length, to be input and the pressure loss of the system to be calculated. This pressure is then what would be used for testing by manually adjusting the valve on the pump outlet of the test rig. The next comes more of the electrical analysis that had to be done. The first is a power curve. A power curve is a graph that shows how the voltage, current, and power change depending on how much sun is seen by the solar panels. This is typically something that is given to you by the manufacturer, but these panels, having come from Kenya, we didn't have much data on them, so they were not with the solar panels. So we had to create them through analysis and the data we did have. These curves can be used to determine the true power generated throughout the day. The graph on the top left is the power curve estimate, and the different lines on the graph show the different percentages of sunlight on the panel. As you can see, the lower the percent of sunlight, the lower the current and power produced by the panel is. So as you go down the graph, the different colors, that represents less solar iridescence seen by the panels. The next part of the analysis we did was the power versus time. So we used the power curve estimate, which gives you just any generic amount of solar irradiation on the panels to give you your power. So what we did is we created a power curve specific to Kenya and specific to Turkana, Kenya. So the power curves give you a way the panels react to the sun. So in order to get the what the power versus time was, we had to use the latitude of Turkana, Kenya to estimate the position of the sun throughout the day. We use this to determine when the pump should start pumping water and to prevent future startup problems. The graph shows that the panel starts seeing sunlight around sunrise, which is around 6 a.m. in Turkana, and it takes about 3 hours for the pumps to reach peak power, which is around 380 watts. They see this for roughly 7 hours a day, and then you decrease until sunset.
So after testing both pumps, we created 2 standard pump curves to better understand the characteristics of each pump. The yellow dotted line along the top of each graph represents the amount of power the pump motors are drawing as the flow rate is increased. The orange dotted lines are the amount of fluid power that can be produced by the pumps as you increase the flow rate. And then the blue lines are a function of pressure and flow rate, and they represent how much flow the pumps can produce depending on the depth of the well that they are placed. So we first wanted to make sure that for a 30 to 50 foot well, which is typical in Turkana, that we'd be able to provide 10 gallons per minute of flow. Both of these pumps easily provided that much flow for much deeper wells, so we were very satisfied with these results. However, each pump required about 1,000 watts of power at almost any well depth and flow rate. This is way more power than 2 solar panels can currently, 2 solar power panels currently being used in Turkana would be able to provide. Looking at the graphs, you can see that the yellow dotted line, like I said, show how much power is required by the pump motors, and the orange dotted line show how much power is actually turned into fluid power. The difference between these 2 curves show how much power is lost through motor and pump inefficiencies. The fact that these 2 lines on the graph are so far apart tells us that neither of these pumps were very efficient. We would hope to see pumps like this be about 60% efficient, and both of these pumps maxed out at about 30% efficient.
So it's evident from the results of our testing that neither of the initial pumps we selected are viable options for CMS work in Turkana. Although both pumps are much more affordable and they can meet the flow requirement of 10 gallons per minute, they require more than double the power used by the current pump, like Sarah explained. Since the existing panels can only provide 380 watts of power, in order to actually use either of these pumps that we tested, CMF would have to purchase additional solar panels for each irrigation site. The cost of these extra panels would effectively cancel out the economic benefits of the lower pump prices. Therefore, our recommendation to CMF is to not purchase either of these pumps. However, by testing these pumps, not only did we gain experience with the importance of testing and verification in the process of engineering selection, but also moving forward in our partnership with CMF, we have a better idea of realistic pump requirements for their systems and have identified multiple alternatives that can benefit CMS work and help them reach even more people in Turkana.
Thank you all so very much for that presentation. I've got 2 questions here from our group, and if you guys have more questions, please feel free to send them my way. This first one is from Hope. Does one have to be trained to use or fix this system, or can you just send a manual with instructions?
So the people that are already in Turkana and using these systems are trained in how they work. The only thing that would be different with our system is that since we've included inverters, since we're using an alternating current pump, we would have to write some kind of instructions for them there. And then we would also want to include all the manuals that come with the inverters and pumps. And then we would also be available for any questions that they have. If we have connections with multiple CMF members, so they can send us an email and we'd be able to help them in any way we can.
Our second question comes from Drake. Is there any purification with this system?
No, there's not. So none of this water is going to be used for drinking. These pumps are purely to irrigate the crops. So there's no purification aspect for this system.
I have another question. Based on your recommendation of not purchasing either of these two pumps, what is your recommendation, knowing that their current way of doing this isn't very sustainable on many different levels? What should they do?
We'll probably just knowing that neither of these pumps work results in itself, because we know that those are not options for them. There are a few other pumps that we've recently decided that we want to look into, so we'll probably continue our research and purchase another pump and test it. And our ultimate goal is to find a pump that we can give them and say, hey, we really think this will work in your system, and it'll be a lot more cost effective, and you'd be able to reach more people by using the money that you would spend on one pump to be able to buy 4 and make a lot more gardens.
Are there any other questions for this group? All right, I should have mentioned at the very beginning of this that Zula and her group won one of the Rise Above Awards for this year's conference topic, which was 2020 Revision, for the way that they revisioned their work with CMF. So congratulations, guys. And we will go ahead and do our technology switch here over to our next set of presenters. So who is going to be sharing their screen for our next? Casey Williams. All right, we are going to try to stick to our time. So I'll give you guys about 1.5 minutes to walk away, go get a snack, and then we will come back and I'll introduce you guys at about 5:20, all right? Casey Williams and Jonathan Wyatt, under the mentorship of Dr. Jeff Giesey, have been working on this project for the last couple years, and they're going to tell us tonight about their rural water supply solutions for Hancock County. It's all yours, guys.
Well, good afternoon, everyone. And on behalf of the group, let me thank you all for being here, and to congratulate everyone else who's presenting today on a fantastic job. And so, as we mentioned a few minutes ago, the theme of this year's conference is revision. And so we'd like to take an opportunity here to tell you about how we've spent this year using some innovative design to improve an old project. Hancock County is outlined here in Figure 1A in blue. And for reference, Milligan College is over here about 1.5 hours to the southeast. And all across the county, there are several mountain springs that serve as water sources for the citizens of the region. And one particular spring, which is shown here in Figure 1B, provides water to the Cedar Grove Baptist Church, as well as to surrounding communities. And originally, water ran downhill from this spring about 1/4 mile, and it was carried by black plastic tubing. It flowed down the hill into a concrete box, which was just outside of the church, and then further downhill before being dispensed beside the nearest road. And Jubilee Project, which is a local ministry organization, partnered with Milligan Engineering in late 2018 to assess the safety and availability of water coming from this source. And from that analysis, it was determined that the water was contaminated with fecal coliforms and also contained high levels of suspended solids, which are both conditions that make water unsafe to drink. In addition to this, the piping that was used to transmit the water was subject to frequent freezing during the winter months, which made the supply of water very, very unreliable. And so by the end of 2019, a design had been developed and implemented that you see here, and it fixed these issues. So Figure 1B is a cover for the spring itself that prevents contamination at the source. Sediment and activated carbon filters were implemented to remove solids. A UV light system sanitized the water to remove microbiological growth, and burial of a 1 1/4 inch PVC pipe with a freeze-proof hydrant attached at the distribution point was able to solve the issue of freezing. However, the design ran into some problems rather quickly, It was discovered that 1-inch PVC pipe had been buried rather than the specified 1 1/4, and this limited the flow capacity of the system fairly significantly. We also found that the pipe was buried to a depth of only 15 inches instead of the originally intended 30. And after conducting an air freezing index analysis based on weather station data from the surrounding area, which you can see here in figure 1A if we scroll up just a little bit. So all of these red points are weather stations that we use to compare to Sneedville. And from this analysis, we determined that the burial depth being half of what it originally was made a catastrophic rupture due to freezing in the system up to 20 times more likely. So in other words, we were taken from well over a 100-year freeze with the original design to just a 5 to 10-year freeze. And in addition to all of these, there were several more areas for improvement. The original design didn't offer us a way to detect if the system was powered or if our UV light and particulate filters were operating as intended or if they needed to be replaced. The interior of the concrete box, which is here in figure B, it had been repurposed as a home for our treatment equipment, and it had insufficient heating for winter temperatures, so the piping inside of the box was susceptible to freezing. We had also incorporated a pressure vessel in the original design, both for water storage and as a means to protect our system from sudden pressure surges. And upon further analysis, we determined that this was located incorrectly within the system and was going to need to be repositioned. We lacked a method that was reliable for getting performance and usage data that would allow us to know how well the system was doing its job and how much people in the community were using the system to get water. And lastly, opening the lid on the concrete box to get access to the equipment, to do maintenance or to add new equipment, became a 2 or 3 person job to move the lid just because of the weight and the shape of the lid itself. And so we knew that the core of our design was strong, but we also felt really strongly that we could do a lot better. And that was what motivated our work this year. And so with that said, we'd like to tell you how we've been able to improve the system so far.
Okay, I'm just going to dive right into the electrical, so buckle up. The carbon filters and sediment filter and UV lamp all need to be replaced periodically, which you do according to manufacturer recommendation. And this doesn't guarantee that those pieces of equipment are going to be providing clean water for their entire lifetime. It's just kind of an average lifetime that they found. So one of our toughest challenges was to ensure that we always have safe water for the entire lifetime of the consumables. And so we tackled the issue by implementing a UV sensor and a microcontroller. So we use the UV sensor to monitor the UV dosage in real time and then signal whenever it's below a certain threshold, indicating that it needs to be replaced. So this could end up, we could end up increasing the lifetime of the UV lamps, but it'll also make sure that if they ever go bad early, that we'll be sure to know. As you can see in figure 3, we were able to implement this by repurposing the existing site port on the UV system, which is on the side. And normally the site port just allows you to see that the UV lamp is operating, and it has a UV blocking lens. So by replacing that with a quartz lens that allows the UV through, the light can get to the sensor and we can tell what type of dosage the water is receiving. So due to our choice of using the UV for disinfection, there's no residual disinfecting agents that's left in the water. And so we have to keep the UV light on all the time. And if there's ever unsafe water that gets past the UV light, there's no way to treat it before the end user gets it. And that bacteria will also stick to the pipes and grow over time. So we decided it was necessary to supplement the disinfection with by using an ozone generator, and ozone can also kill bacteria. And so the ozone will sterilize the down system pipe, and so long as unsafe water doesn't re-enter, then it should be a safe water system. But the problem is that there's several different ways that the unsafe water could get past the UV, including if there was insufficient UV dose before the light was replaced, if there was a brownout, or if there's a total loss of power. So the microcontroller helps to implement and signal when one of these situations arises. We also use the microcontroller to monitor the differential pressure across the carbon filters and the sediment filters, which help us to know when they need to be replaced instead of just doing it every 6 months. Another aspect that we looked at electrically was the insufficient bury depth of the pipe, which drastically increased the risk of freezing. So our solution was to implement a solenoid valve that can open or close based on temperature sensor readings from the microcontroller. And then we can auto trickle water through the system, which drastically improves system tolerance to prolonged freezing temperatures. And lastly, to assist in the implementation of the new electrical design and development of the microcontroller code, I made a GitHub repository to establish these diagrams that you see here so that they can be maintained and improved in the future. And it also just helps to understand what's going on in the system, because as you can see, they're pretty complicated diagrams, and it requires a lot of explanation for what's going on in the code. So there's a lot of crossover between mechanical and electrical design aspects. For instance, the instruments that monitor the mechanical design performance, I also read into our microcontroller and make decisions on what our system is going to do based on that. So I'd like to go ahead and hand over the reins to Sterling to continue discussing the mechanical design considerations.
There we go. All right. Thanks, Giesey. So when it came to revisioning the mechanical side of this project, we added many instruments to read and collect data. A pressure gauge was used to track the pressure of the water within the system. We used a differential pressure gauge to detect pressure drop across the large debris in the carbon filters to ensure that they're working properly all the time. And we also used a flow rate reader, is currently being used right now to track the system's water output and usage. There's also a couple other instruments that are being used to track the amount of energy being used in the system as well. So during this project, there were two pre-existing issues that Bo kind of hit on. One of them came in the form of a large boulder that had pinched and cracked the line near the spring box after it was placed on top of the PVC line. So after breaking up and removing this some 500 odd pound boulder, we replaced the line at that location. And then after that, we found that there were rocks within the line that were giving us a blockage. One of the PVC couplings that was underground, that was only 15 inches. So after removing these two issues, we were able to increase the flow rate greatly from about 1 gallon a minute to 4.5 gallons a minute. So with this new information, the storage tank wasn't really needed for storage so much, but it was still very important to be used as a pressure vessel to protect the UV light from water hammer coming from the upstream line in case of sudden water stop at the outlet. So it was repurposed and moved behind or from the downstream before the UV light. The other thing was that the pre-existing lid, it was very heavy and made to go over top of the concrete box. So it was very cumbersome, had sharp edges, and like Bo said, required 2 or 3 more people to move it. It was just a chore to move. So as you can see in figure B, the new lid design utilized insulation to keep heat within the box and was only about 100 pounds and was hinged to the back of the box. So this still presented a safety issue when the lid would close. So to overcome this, we used gas struts mounted on both sides of the box to make the lid very easy to open and also ensure that the lid closed with a force below the force required to break a person's fingers, because we didn't want that happening. So from doing a little bit of research on test data, utilizing a research with cadaver fingers, we found this force that was in the neighborhood of about 67 pounds of force or so. And we did not conduct those tests ourselves with cadavers. We did not steal them, but they were, that was research that we used and found online. So yesterday we actually gained more information from this and found that the design implementation that had been set up showed that it only takes about 10 pounds of force to open the lid, and the lid closes with a force of less than 5 pounds. So we've met those requirements, which is good. And then lastly, the angle of the lid, when it came to the gas struts, we wanted about 60 degrees or so in order that our tallest member could stand up in the box and work on the instruments and adjust things as needed. but during the implementation of the lid, we were able to open up the lid all the way to 90 degrees. And this gave us a lot more room to work in that space as needed to fix things or adjust things. So with that, I'll let Jonathan take care of the conclusions.
All right, thank you, Sterling. So based on everything that my colleagues here have mentioned today, we ran into our fair share of complications with this project. Anything that possibly could have went wrong did, or at least it felt that way. Some of these were self-inflicted, while others were out of our control. Regardless, all of those complications came with their own teaching aspects and moments of humility. These taught us that even the most frustrating problems can be the most rewarding. Even now, the circumstances surrounding the coronavirus pandemic have caused us not to be able to finish implementing our complete design as planned. However, the primary objectives of providing clean water supply and improving availability have been achieved. For our future work, it includes fitting the UV sensor circuit, integration of a microcontroller code, wiring the new electrical box and signaling panel, along with the installation of the trickle solenoid. The addition of the UV sensor and microcontroller will allow for a clear indication of when the water is reaching unsafe drinking conditions, as well as when the consumables, such as the filters and the UV light itself, need to be replaced. These design limitations will allow for improved confidence in water safety for not only the provider, but also the end user. The implementation of the trickle solenoid in conjunction with the anti-freeze heater that is already installed would ensure that our concerns of long-term thermal reliability have been addressed. To further our assessment of this project, the implementation of a data logging system is anticipated to substantially improve long-term system availability. These improvements to the existing rural water supply should allow for a reliable and safe drinking water source for years to come. Altogether, this project aims at furthering the partnership built between Milligan College and Jubilee Project with the intent of improving the lives of underserved populations. Before I close, I would like to thank our faculty and our sponsor, as well as Nathan Yunt, for their time and support with this project. At this time, I would like to open up the floor for any questions if anyone has any.
Thank you guys very much. I have one comment from Dr. Carolyn Carter here that I'll read off to you. She says, Milton and I were involved with hosting the regional CTE, Career and Technology Education Teachers, on campus on March 12th. One of those faculty members was from Hancock County. Her church was the church where this team did their work. She was beyond ecstatic with the work this team did and was very appreciative of their work. Are there any other questions? You guys can feel free to unmute your mic and ask.
I know it's a long distance where this pipe is being run down to the supply. Is it feasible, in your opinion, to cover the pipe over? I know digging it out, you don't know whether there are rocks underneath. And although you didn't say it, it was a contractor issue. It wasn't your fault on this. Would it be feasible to cover it over or insulate it in some way to lessen the likelihood of freezing?
I would say that in theory, I think it would be feasible. In practice, it would be a very, very big job. The distance is not so much the issue as it is the terrain. You can sort of see from the first picture of the spring, it's not the sort of place where you would be able to drive if you didn't have four-wheel drive, if you weren't able to get something rugged back into a wooded section. So I think in the future, if that burial depth presents serious issues, and if the powers that be decide that they would rather pursue that rather than attempting to rebury the pipe deeper, I think it's possible, but I think ultimately financially and the labor that would go into it, just because of where it's located, would be fairly substantial.
Thank you.
Any other questions? All right, thank you guys very much. Our next presentation will start at 5:40. So you've got a couple minutes before then. The group that's going to go next, go ahead and whoever's going to share your screen, please go ahead and pull it up so that we can be ready to go at 5:40. Thanks, guys. We are on to our third presentation for the evening by Mitchell Bronstetter, Isaac Carson, Doc Maines, and Mihail Nakoff. Their mentor for this project was Dr. Jeff Giesey, and they will be talking tonight about their clean water system in Kenya. It's all yours, guys.
Thank you. First, I want to say thank you say great job to the first two projects. It's been really cool working alongside them and seeing all the progress that they've been made. I want to also thank everyone for taking the time out of their day to come and listen and see the work that we've done this year. For our senior design project, Isaac, Doc, Mihail, and myself, we have been working on a clean water system in Sambalat, Kenya. For some background information, last year, Dr. Yola reached out to Dr. Giesey and about possibly helping out with a water system in Kenya. Dr. Giesey took a trip to Sambalat, Kenya, in the picture below, and found out that the water source had been dried up. And this was used by the primary school there, which had about 1,000 students and faculty members. And the school is also located in a community of around 6,000 people. And at the beginning of the school year, a new locally funded pipeline was introduced to the community. And this pipeline would provide water to the community, but during field testing, it showed that the water was contaminated. The water had microbiological contamination in it. The water from the source had to be boiled before consumption, and this can be an exhausting process for lots of members of the community. So oftentimes people won't boil the water and will just drink it from the source. This can cause a sickness to children and adults. So having clean water here is something that can really be overlooked and something that we really wanted to help with. So Milligan engineering students, we partnered with Milligan and some seminary faculty and the administration of the Sambalat Primary School to help improve the water availability and quantity. And in our research, it evolved around designing a system that delivers clean drinking water from the pipeline to the primary school and surrounding community. And Doc is going to explain the design constraints we had.
Thanks, Mitch. I'd like to take a moment to talk about some of the design constraints and also cultural considerations that became paramount within this project. Along with common design considerations such as safety, cost, and the amount of water that is provided, a few more subtle considerations became major constraints within the project. Because of cultural differences between American and Kenyan society, two major cultural considerations played a large role in project decisions. Because the community was accustomed to natural spring water, they had requested that our design would not add an unpleasant chemical taste. Also, our design was shaped by the hope that the community of Sambalat could implement our design and recommendations without outside assistance. In this, they would have the dignity of choice and self-sufficiency. Other design considerations focused on meeting this goal in a sustainable way and the project also being independently feasible by the community. Some of the other design constraints that were present within the project also included keeping implementation and maintenance costs low, making sure that as much as possible the components within the system were locally available, maintaining enough water and flow rate to meet the needs of the school, and also meeting safety regulations that dealt with turbidity, chemical presence in the water, and also microbiological presence within the water. In these, we strove to meet those standards and ensure that the water was clean. With all that being said, I would like to turn it over to Mihail to talk about their proposed solution to the problem.
When talking with our partners in Sambalat, Kenya, there were concerns about any system that was reliant on electricity. The reliability of the electricity in that area is low, and solar panels are, especially with batteries, are very expensive. So that guided us towards a completely gravity-fed system. Our system first has a coarse filter and then a sediment filter, which removes the particulates. So that sediment filter is actually a spool of string, which filters those out and uses the same container as the other filter later in the system. We decided to use the chlorine to kill the microbiological contamination. So because we wanted to keep away from electrical power, we were able to find a dosing system that used the energy from the flowing water to pump the chlorine in the right ratios. So the water then flows into a tank that is sized such that the water sits there long enough for the chlorine to take effect. The water then flows out of that, and because of the community's concerns about the chlorine taste, we have included 2 activated carbon filters, which are able to remove the chlorine from that. We included a flow meter, in order to determine when those filters need to be replaced. And once it's gone through the system, it should be easy to distribute to the school and the community. The system was designed so that it can be repeated, and it is small enough to not be an overly large financial burden on the community. By giving the community the designs for the system instead of implementing it for them, we hope to foster their ownership of the system and their ability to develop their community without relying on outside aid.
So I'm going to talk about the testing that we were able to do on the system. Most of the testing we were able to do focused on chemical levels that we expected to see in different parts of the system. And mostly we were looking to see how much of the chlorine activated carbon filters would be able to remove. Chlorine is something that almost all activated carbon filters can remove, but very few of them give you the data of exactly how much it removes. And we wanted to remove enough that it wouldn't be able to be tasted at delivery points. So to do this, we took samples of tap water and added chlorine to get to the levels we were expecting to see in our design, which is around 4 parts per million, because that's what is considered normal for disinfecting water like this. And then after we added it, we measured it to see that it was close to what we were expecting, and we ran it through an activated carbon filter, and then measured it again to see how much was removed. And starting at around 3.5 parts per million, when we added the chlorine, it removed enough that we couldn't even measure it. Down here you see the results. On the left is before it ran through the activated carbon filter. In the tests, basically, the darker the color is, the higher the concentration of chlorine is. And then on the right is what it looked like after running through the activated carbon filter. And that was so clear that we couldn't even, it was more clear than the lowest amount it can measure, which was 0.1 parts per million. So it removed basically 99% of the chlorine that was in the water. So that was a good proof of concept that removing chlorine would work well in this situation at removing the chemical taste. And then some other testing we did as far as chemical levels was specifically looking at boiling water to remove any chlorine that's left after the activated carbon filter, because we were suggesting that the community also get a chemical test that they can use there to assure that the chemical levels when this is implemented are safe. But to use these tests, you have to clean out the test tubes with deionized water, which they don't have access to. So we were looking at boiling water as a way to circumvent this, and those tests were positive as well, with the levels that we're expecting to come out at the distribution point. Boiling removed anything that was left over, so that looks as like a possibility for that. Then we have a lot of other testing that was planned, but we were unable to get to, but we have drawn diagrams and testing procedures to give to our professors and possibly the students next year to do the testing on this system. And those are mostly just verifying their performance characteristics and making sure there are no issues with the design that we're suggesting. And most of those tests, some of those tests are the performance of the chlorine doser itself, looking at how accurate and precise it is at dosing chemicals, making sure that there is no danger of dosing higher than what's safe based upon standards. And then the other thing is looking at the doser to see how it performs if the flow rate is lower than what is prescribed to the part, meaning if the bottom is 1 gallon per minute, if there's a leak somewhere and you have half a gallon per minute, how does it perform? And basically what we're checking there is to make sure that if the flow rate goes below what it can handle, to make sure that the device doesn't allow flow through it, and it doesn't just allow water to pass through it without it being treated, because then you would just end up with a tank full of water that hadn't been treated at all. The next thing is looking at the flow rate through the system. That's mostly delivered flow rates, because our test design rig has the same amount of head that we're expecting out of the implemented design. So whatever we measure in the lab should be similar to what would be in the field. The next would be the performance of the activated carbon filter, and that's over time. So we know that when you first hook it up, it should remove 99% of the chlorine, but how does that look a month later, 2 months later, up to a year later? And then the last one would be water quality, just to ensure that after it's sat the amount of time it needs to, that it has disinfected the water, and now you don't have microbiological contaminants that would cause people to get sick. Below are the references that we use to determine our parts per million of chlorine in our design. Those come from the World Health Organization and the Kenyan Ministry of Health. And both of those agree that 5 parts per million is kind of the maximum that's suggested. And then it also talks about the maximum that can be tasted, while the minimum that can be tasted is about 0.3 parts per million. So that's what we're looking for at delivery. Special acknowledgements go to Dr. Harrell for being our technical advisor, and Dr. Giesey being our advisor through all this, and then Dr. Elolia, who was our main contact when we were asking questions about the community and what everything looked like there, because he's from Sambalat, and he got us in touch with some other members of the community to ask them questions. So this project wouldn't have been possible without him. That's all we have. So if anyone has any questions.
Thank you guys very much. I'll open the floor for questions. Feel free to just unmute your mic and hop in. Since nobody else is asking questions, I guess I will. You guys talked at the very beginning about this as being something that you hoped a lot of the materials could come from a place where they would be able to access them easily. What's your analysis of these filters and how easy are they going to be for these people to access?
So the specific filters we picked out in this proposal are available from a Kenyan manufacturer, Davis and Shirtliff. Specifically, they're headquartered in Nairobi, Kenya. And they also have smaller satellite sites that are within a few hours drive of this area.
And the tank also comes from a Kenyan producer, and we checked that they delivered to this particular part of Kenya that Sambalat is located in.
Awesome. Any other questions? Okay, I have another one. The chlorine that you used in your testing, did you just use straight pool chlorine?
Bleach, actually.
So not actually pure chlorine.
No, a mixture.
Okay. Any other questions? All right, thank you guys very much. Our next presentation is at 6 o'clock. Our second to last presentation tonight comes from a senior chemistry major, Graham Denton. And he is going to be talking to us tonight about the work that he has done for the last couple of years on determining coatings for wood that can sustain water resistance. Graham is a chemistry major with minors in graphic design and art. And so that kind of this project comes from his intersection between the two. Graham, it's all yours.
Well, thank you, Dr. Mudrack, and a special thanks to you for being strung along through this project over the semesters. I have to give you a special shout out for that. So the first thing I want to talk about is wood structure. So wood structure is composed of cellulose, which is about 70% of wood. And to the left, you can see a figure of cellulose chains. Hemicellulose, which is a subtext of cellulose. Lignin, which is kind of a building structure, so that way the hemicellulose and the cellulose can build off of each other. And small aromatic compounds and aliphatic compounds, and also has terpenes and terpenoids. The thing we want to focus on is cellulose. Cellulose is the main component of our wood structure. So a kind of introduction to this is preservation of wood. So the preservation of wood has been around for a very long time. It's been archived as using different dirts, different natural materials to try to find a way to preserve wood that we need to preserve to keep things in structure and to keep things in balance. Common wood coatings include lacquer, shellac, polyurethane, varnish oils, and wax. So what coating does is it helps protect the wood. It helps protect the wood from insects, fungus, water, and fire damage. And so a lot of these things are the common types of materials that you would see in interior wood coatings. So there's a difference between treatment of wood and coating of wood. Treatment of wood happens during the drying process of wood. So as soon as the wood is cut fresh from the timber, it is treated with a certain chemical to help maintain a water resistance level fresh off of the tree. And coating is something that you add on top of the treated wood to help maintain the balance between the treated wood and the coated material. So one of the common types of treatment of wood is the acylation of wood. And what happens is you get an acetic anhydride and you add the OH bond of the cellulose and you attach it on. So what happens is there's a shift of electrons that go on to where the acylated wood is now a hygroscopic material, which gains water resistance, and it creates acetic acid, which can easily be eliminated through the wood process, and it doesn't harm any of the other materials that are found in wood. So this is really important because this is part of the treatment of wood to help the water resistance within the wood. So what happens when moisture is absorbed into the wood is the cellulose chains, they begin to shape. They begin to expand and contrast. And this is really bad because it can cause warping or splitting in wood. So with how all this happens is it's not only just once where it expands, it constantly expands and contracts to create that warping or splitting effect. So this is important because wood holds up your homes, it holds up sheds, it holds up furniture, it holds up things that we hold near and dear to our hearts that we don't want to break down after a couple of years due to faulty wood materials or faulty coating materials. And it also is important because a lot of the coating materials out there on the market are primarily man-made instead of natural-made. So there's a reason why we need to switch from man-made to natural-made to try to get a more greener product in our system of using coating with interior wood products. So the first man-made material is actually disodium octaborate tetrahydrate, or DOT for short, and I'll be referencing that as DOT for the rest of the presentation. So what it is it's actually a mined mineral that comes from mountains, and it is mined and welled out, and you have to then put it in a solution to make it sprayable onto wood coatings. And as you can see, it's a borate ring with a lot of negative oxygens and a lot of OHs, and it also has some sodium ions. And what happens is this: in the sodium ions, it actually helps create salt, which is also a natural preservation of wood. And the negative oxygens allow it to have more hygroscopic properties to allow the wood to be secure from this. So the thing about how this works, and the thing about how all coatings work, is it works to create a less of an equilibrium between the water and the wood. So one of the things that you have to look out for is water resistance, but it also creates an equilibrium between where water can be absorbed by wood and water being released that causes the splitting in the coating. So normally what happens in this type of DOT is it creates a suspension. So think of milk on a table. Instead of the actual coating being soaked into the wood, it's actually laid on top of the wood to create this kind of boundary between the treated wood and water from the outside. So it acts as almost as a buffer for water. And it also helps from blocking the acetylation to be changed, because when excess water gets into the acetylation process, it can also chemically modify the structure to create more or less stable chemicals. And it also helps bind to wood properties to allow that acetylation to stay put and to stay natural. So in my experiment, I tried coating wood with 5 different options. One option being a control where there was no coating material whatsoever. And then I had tung oil, which is a common interior household item, a linseed oil, which is another common interior coating, clay, which they used in ancient times, just to give a perspective to see if that worked, and DOT to see how that would stand with all these natural materials. I used oil because of the hygroscopic properties of a long-tailed chain, which allow it to have hydrophobic abilities. So the next thing I did is I would soak wood for a 24-hour period, and then I would record the weight, but I would soak the wood every 7 days. And I plotted the data for over 6 weeks. So it gave out every 7 days, I would soak the wood and then map out the weight every 7 days to try to reveal a pattern. So these are my results. So I wanted to look for rates of change. When you look for the rates of change, you want to look for the equilibrium. If it's shifting too much, if it's dropping too fast, you're looking for those drastic measures to see if the equilibrium has shifted in any sort of way. And you also want to look for specific patterns, because after a couple of weeks, you start to notice pattern changes and you want to try to correlate what that means within the data. I also wanted to look at specific drop rates, again, kind of seeing if the equilibrium was affected in any way or if there were better solutions by specific drop rates. And I also looked at, was there water loss over the weeks? Was there a significant decrease each week of water being gained or lost? So for the untreated, as you can see, it actually completely started to do equilibriums when they were soaked and then put out of water. So that kind of splitting wood started to happen, and that warping of wood started to happen because there were higher rates and lower drop rates. So the first couple of weeks, there were kind of no patterns being shown. It was all kind of all over the place because the wood was still equalizing with the water rates. And after about the third week, you kind of see pattern changes and you could see where the equilibrium was happening. But these drop rates were too low and the gain weights were too high. So on my x-axis, I have the time it took, and the y-axis is the grams. And in between each line, you can see the week that I went by. So clay kind of offered an interesting result as well. While it helped the drop rates, it wasn't really effective in creating a different slope within the graph. So the thing about clay is it created a drop rate of water, but it also allowed equilibrium to still set in at a fairly moderate rate. The thing that you need to look for is a high in the first day slope that kind of lingers off on the second and third days. So for tung oil, it worked a little bit better, but you could see that water was still being retained and naturally being soaked or taken out of the wood. So you wanted to see more of a kind of a drastic drop when you looked at these. So unfortunately, tung oil didn't really provide any really conclusive evidence that it was the best. Now, when you get to borates, you can kind of see a difference. You can see where the slope starts to drastically decrease after the first and second days and start to level out the rest of the week. That shows that when you drop the rates, it holds the water retention and then it levels out to slow down the equilibrium of the wood. So that's the kind of pattern we're looking for in trying to hold out on the water retention and gain less equilibrium between water and wood. Now, linseed was probably one of the most shocking results to me because as you can see, the slope rates were very high throughout the first couple of days and then it leveled off really well. So that kind of showed me that linseed oil was making a breakthrough within the experiment. And you had to monitor these for over several weeks because as you can see from my first and second week results, they're not giving any conclusive data. All it is the wood is trying to equalize and you can't see any patterns changing or you can't see any patterns emerging. So this is a full graph of the results put together. So as you can see, the untreated was very wild and created a pattern where equilibrium was all over the place, causing that splitting and warping. But if you can notice that the linseed oil actually had a lower retention rate, a lower water gain than the dot did. So it shows that the linseed oil actually maintained less water than the dot. So what I decided was linseed oil showed drastic results after week 2. We could see that pattern of water being released out of the system and the equilibrium being shifted. And you can also say that clay, tung, and untreated started to just stay consistent the whole entire time of holding that equilibrium and retaining water within their system. Now, the first and second weeks, there's extreme drops due to high resistance, but also that equilibrium is setting in because when it rains, it doesn't only rain once. So you have to test multiple times of water so you can observe that pattern because if you only did it for the first and second weeks, you really wouldn't know what to expect. And as you can see, once the equilibrium started to kind of settle down, you could see patterns emerging. And as I mentioned before, the untrial rates were the warping and expansion, as you could notice when it was being soaked and then taken out and weighed. So for my conclusion of this project, tung oil was the worst natural coating because it held that retention rate and it held that equilibrium. So it wasn't being released into the system effectively. Linseed oil was the best natural coating because it had the high retention rate in the first couple of days and a low equilibrium slope in the last days leading up to the soaking. There are other solutions to natural wood coating that can be emerged from this project, and there are other different types of coatings that we can use like waxes or specific natural polyurethanes that we can have. And also what I learned is it's important to follow through after the first and second weeks, because you can really discover a pattern throughout the whole entire experiment if you stay consistent, and you can see where equilibrium is being settled in for the rest of the time. Thank you.
Thanks, Graham. I've got one question for you in the chat, and if anybody else has any, you can feel free to send them to me or unmute your mic here in a minute. This comes from Doc. Do you know how the effectiveness of these coatings compares to pressure-treated lumber?
So I didn't specifically look at pressure treated lumber. I saw research for it, but I mainly focused on chemical treated lumber instead of pressure treated. So that's something that will definitely have to be explored, because there are many different treatment options besides a chemical treatment. So I think it would be interesting to do a series of these tests over different types of treated wood to see if there's any difference in it.
I have another question from Sterling. If I understand your graphs, then linseed is better than dot. If so, then why do people use dot? If that's a dumb question, don't ask it, please.
If that's a what?
If that's a dumb question, don't ask it, please.
It's not a dumb question. So
okay.
Linseed oil is not as used as dot, because dot was kind of one of the first things that really worked, and it was known as a cheaper material to make. So the mining process was pretty cheap, but linseed oil is mainly used for a lot of interior coatings, and dot was kind of used more for around the house coatings as well. And I don't think a lot of people could assume that you could put linseed oil on an interior piece of wood and still have the same effect that dot would.
We got a question from Eleazar. What species of wood did you use for the tests?
I used a hardwood. So a hardwood has less terpenoids and terpenes in it. So it created less variables for me. So, and really when you talk about woods, there's only two major types that you have to be concerned about, and that's hardwood and softwood. So hardwood is something that that has less chemicals in it, while softwoods have more terpenes and terpenoids in it. A lot of hardwoods is used for interior framing, and a lot of softwoods is used for interior modeling. So kind of furniture making, all that good stuff.
Eleazar has a follow-up question. Was the species of wood you used for the test fresh cut or kiln dried?
So my specific project, it was fresh cut. It was not kiln drying. We tried that at first, Dr. Mudrack and I did, and we noticed that there was a lot of splitting going on being dried. So I thought one of the best solutions to do would just be to let it be natural, because that's how you would put up a home. You wouldn't dry it after it's being treated, so you would just let it be natural.
I have one more question from Randy. I noticed a discontinuation in data points in some of the graphs. What can this be attributed to?
Me forgetting to weigh it that day. Sorry, Randy. That's just the honest.
See how you were going to answer that one.
Huh?
I was waiting to see how you were going to answer that one.
Yeah, I'm sorry, Randy. That was just that was error on my part, and I really wish I would have remembered to weigh it. But when you do have projects like this, sometimes you forget, and it's a whole lot more of a nuisance to go back and restart everything than just follow through with a couple of data points missing. And a lot of the data points that were missing, you could still see the pattern of what was going on.
I will also point out he did restart this at least twice.
Yes.
So this is the most complete set of data we've got. I have one more question for you, Graham, from the chat. Do you think you would want to continue this research in softwoods and compare the difference?
You know, it's a very interesting question, because you would think that softwoods may provide a whole different data point or a whole different data set, and they may. But I really wanted to look at framing, and furniture is more used of softwood. So if you were more into furniture and more into the effects of how furniture would be treated with water resistance, then I would say absolutely go test softwood. But I was more worried about interior walls and interior housing. for my project.
I have another question from Drake. You just kind of answered this a little bit, but what was your inspiration for this project and why is it special to you?
So my whole entire collegiate career, and Dr. M can say this, has been crazy. I am a chemistry major with 2 art minors wanting to go to architecture school. And a lot of people kind of give me a look of, what in the world are you doing? But I really love architecture. And I'm going to hopefully go to master's school for architecture next fall. And I was really inspired to do this project because it was a blend of architecture and a blend of chemistry. So I was really excited to do something that could hone 2 things in that I really love to explore and love to try to work out.
All right, thank you so much, Graham. As your advisor, I can say you did a wonderful job. Good job. We have one last presentation in this section today. So Hannah, if you want to go ahead and share your screen once Graham has his off, that'd be great. All right, and we will just go ahead and jump right in here to our last presentation of the night. Graham, you want to go ahead and mute your mic for me? All right, our last presentation today actually comes from the Outstanding Undergraduate Award winner for the year. Ms. Hannah Rogers won the Outstanding Undergraduate Research Project for this year. The paper that she wrote was very well put together. Hannah and Madison have been working on this project for the last 1.5 years or so. And the reason Madison isn't on that paper is because she will actually be continuing this work this summer. So the data you're going to see today is data that Hannah got over spring break, right before all of the craziness started and the world fell apart. So Hannah and Madison, please tell us tonight about your synthesis of unnatural dipeptides against Pseudomonas aeruginosa.
Good afternoon, everyone. First off, Hannah and I would like to thank everyone for being here, as well as congratulate all those who presented today on their hard work and research over the past semesters. I'd like to start off by giving you all a little background about our project. So our research topic spans far past the 3 semesters that we've participated in 499 research. Our topic is one that has been of interest of other college students across the United States, as well as in Cuba. So cystic fibrosis, also commonly referred to as CF, is a genetic disorder. More specifically, CF is an autosomal recessive disorder. So this means for those who have this type of medical condition, they had to obtain a copy of the gene from both parents. Although both parents must be carriers of the CF gene, they do not, however, have to have CF themselves. Currently, there are 40,000 reported cases of CF globally and 30,000 reported cases in the United States. And the reason that the US has such a large number of cases is because we have better testing and screening capabilities. So the CF gene is one that affects the function of the cystic fibrosis transmembrane conductance regulator, which is also referred to as CFTR. So CFTR itself is a protein that is responsible for the chloride ion channel that is located in specific tissues. So when working properly, this channel targets and moves chloride ions across the cell membrane through a gate-like channel. So in patients with CF, the chloride cannot pass from one side of the cell membrane to the other because the CFTR channel itself is faulty. And this results in a mucus buildup on the cell membranes. So as you can see in the figure, cystic fibrosis itself is a systematic disease, which means that it affects many different systems within the body of the patient. So the diagram shows that CF can cause problems specifically to the lungs, the pancreas, which causes a unique type of diabetes, intestines, and the reproductive organs. For our research, we're going to focus on the lungs. And in the lungs, the sticky mucus serves as a breeding ground for infections. So the most common bacteria that causes infections with the lungs in patients with cystic fibrosis is called Pseudomonas aeruginosa. So as you can see in the figure that 80% of patients who have bacterial infections in the lungs have a Pseudomonas aeruginosa bacterial infection. And once contracted, CF patients will have this infection for the remainder of their life. There is no cure for it. If patients have been diagnosed with the Pseudomonas aeruginosa bacterial infection, they will be placed on antibiotics. Today, the two antibiotics used to treat this infection are topramycin and aztreonam, which is more commonly known as Kristin. So in an attempt to increase the effectiveness of the antibiotics that are available to them, the physicians will more than likely implement a plan where the patient will spend 1 month on topramycin and 1 month on Kristin. And they do this because when a bacteria is exposed to antibiotics for an extended period of time, we begin to develop what we call antibiotic resistance. And antibiotic resistance is when the bacteria is exposed to the antibiotic so much that it can actually inhibit the effectiveness of how well the antibiotic works. So this is where our research comes in. So our goal is to try to find more antibiotics that will combat the Pseudomonas aeruginosa bacterial infection to give cystic fibrosis patients more treatment options.
So what we chose, or our antibiotics are made of, are what's called dipeptides. And a dipeptide is where there's 2 amino acids put together by a peptide bond. So why dipeptides? Well, first off, Pseudomonas aeruginosa is a gram-negative bacteria, which means there's a negative charge associated on the outside of the bacteria. And our dipeptides in certain environments in our body have a positive charge. As all of us know, negative and positive charges attract to one another. So the bacteria and the dipeptide will adhere to each other closely. Another reason why this is effective is because the cell membrane of a bacteria is made of lipids, which is another word really for fats. And in our dipeptide, indicated by the blue arrows, are lipid-like things. So they like lipids, and they can penetrate lipids very well. So they can penetrate the bacteria and cause it to lyse and be destroyed. So how do we make these dipeptides? Well, our first step was just prepping the resin, and a resin is another word for bead. And in solid phase peptide synthesis, a bead is important because it allows us to build up our product very easily. Our second step is alkylation, and basically what that means is that we're adding the R1 group here on the second side of the arrow, and that's basically we're making our first amino acid out of our dipeptide. Like I said, dipeptides are made up of 2 amino acids. And the amino acid that we're adding is called fluorophenylalanine, and we added either 2-fluoro or 3-fluoro. And what that means is it just changes the position of the fluoro group on the amino acid. And what this is testing is the 2-fluoro better against the bacteria, or is 3-fluoro? And the third step is hydrolysis. So what this basically does, it's going to take the 2 phenyl groups that are represented by the pH on the left hand side of the arrow. It's going to remove that and replace it with an amino group to prepare for the next step.
So step 4 is what is known as acylation. So in this step is where we will attach the second amino acid to make the dipeptide that Hannah had talked about already. So as you can see on the left side of the arrow, the R1, which is the first amino acid, and now on the right side, you can see that it has both R1 and R2, making it a true dipeptide. So this step is important because it also allows us to alter the stereochemistry. So stereochemistry, for those of you who have not had organic chemistry, has to deal with the 3D structure of a molecule. So as you can see in both alanine and valine, there is a solid wedge below the arrow. This means that the molecule is pointing towards you, which makes them both L amino acids. In D-valine, the molecule has a dashed line, which means that the molecule is pointing away from you, which makes it a D amino acid. So not only are we trying to test the various amino acids, but we're also trying to manipulate them to test and see if their 3D orientation affects how well they fight the Pseudomonas aeruginosa bacteria.
So our last step in creating our products is just removing that resin or bead that we talked about earlier, and now our products, our crude products, are ready to be tested. So our next step was purification. So we took a small amount of our crude product and we ran it through the column on the left-hand side of the PowerPoint slide, and we collected 14 fractions in little test tubes. And to figure out where our pure product was in the fractions, we use what's called a TLC plate. And that's seen on the right. And this is a TLC plate of our crude products. And if you can see the little dots present there, that basically just shows the location of our crude products. So when we do a pure TLC plate of our pure products, we can look at the dots, and if they match up, then that's where our pure product is. And we pulled those fractions together that contained our pure product into one container to test. So our last step in our experiment is the biofilm assay. So what this basically does is we're testing our products, our crude and pure, in the bacteria to see how effective they are. In the F column, you'll see in the very bottom column is there are controls, and in F1, it's just the media and there's no bacteria present. In F2, it has what's called 10% DMSO, and all of our products have this in it. So in this well of F2, it only has 10% DMSO and the bacteria. So that means that the growth should not be inhibited at all. And the other controls for F3 and F4, they have tobramycin and casein. And in our last control is just 4-fluorophenolalanine. And in our D and E columns are our pure and crude products. And in the D column, there's 2-fluorophenolalanine. And in the E column, it's 3-fluorophenolalanine. So why are these wells purple? Well, first of all, it includes crystal violet. And crystal violet is a color stain that closely adheres to bacteria. So the more purple it is, or the more concentration of crystal violet that is present, the more bacteria that is present. And then that means that that product didn't inhibit the growth that very well. So to show our results in a graph form here, I use what's called a UV vis machine, and I measured the absorbance in each well, and I used an equation to find the concentration of crystal violet. So to break down this graph, basically, an orange are our controls, and the 10% DMSO that I mentioned earlier should have should not inhibit any growth of the bacteria. So anything above 10% DMSO concentration did not do well. So you see in the blue, that is alanine. So it did not inhibit the bacteria very well at all. So in yellow and in pink, you can see below 10% DMSO, they inhibited the bacteria to some extent. And in the yellow, this is valine, and in the pink, this is D-valine. And another important thing to point out is that aztreonam did not inhibit the bacteria as well as D-valine did. And that's because in a normal circumstance, when you're prescribing these antibiotics, aztreonam is given 3 times a day and tobramycin is given twice a day. And in our project, we only did 1 dose in a 12-hour period. So that makes a difference. Also, the last thing I like to point out about this graph is that all the rest of our controls had the least amount of crystal violet concentration. That means they had the least amount of bacteria. So that means we have room to improve our antibiotics. So this is a chart of a one-tailed t-test for 2 independent means. So what I basically did, I wanted to look at the significant differences of the concentrations to see if there was an actual significant difference. And in this chart, you can see that alanine and D-valine, there was a significant difference in concentration. So that means D-valine significantly killed the bacteria better than alanine. Also, you can see that when it came to the 3-fluoro position, D-valine was significantly better than valine. Also, in the last part of the chart, it said you can see that when it comes to D-valine, 3-fluorophenolalanine is better than 2-fluorophenolalanine.
So as I had mentioned before, other schools have also been a part of this project, such as Goshen College, Colorado College, IUPUI, and a university in Cuba as well. All the data from each of the different universities are put into one large database, allowing us to create a bigger impact together than we would each individual school working alone. At Milligan, this project was really started last year by Kelly Guerin and Andy Lamb. Their results showed that D stereoisomers worked better than L stereoisomers, and that 2-fluoro worked better than 4-fluoro. Our results showed that 3-fluoro worked better than 2-fluoro, so we are interested in running more trials to see if these results continue and if we can find a combination of a D stereoisomer and a fluoro position that would work the best to inhibit the growth of Pseudomonas aeruginosa. In the future, we would also like to run 3 fluoro and 2 fluoro through the UV vis and use them as controls just like we did in the 4 fluoro. We were not able to do this prior to this presentation because we do not have access to a lab currently to do so. We would also like to better improve our purification process. So far, we have only used physical filtration methods as we ran our products through a cotton ball-like material. However, we are interested to see if we do this more than one time, or if we try to use a chemical method to purify our products, if we could establish more of a difference between our crude and purified products. In regards to more trials this summer, through the support of the Ledford grant, I will have the opportunity to run even more testing of trying to find different combinations of amino acids in the dipeptides to try to strengthen our research here at Milligan and to contribute to the overall database. Next year, Aria Binkley, Callie Pittman, Amy Hyder, and Danny Bryant will also begin working on this project as well. However, they will add a new element to this project, which is quorum sensing. And quorum sensing is how bacteria communicate with one another. So they're going to see if they can disrupt the communication, if it will alter the overall effectiveness of the antibiotic as well. Before closing, Hannah and I would like to thank Dr. M for all of her help and support throughout our undergraduate research project, because none of this would have been possible without her. Thank you.
Thank you very much, girls. Casey Williams has a question. Casey, you want to unmute your mic?
Yes, I was wondering if you all had considered using like molecular modeling to try to figure out like common patterns for why one molecule works better than others, and if you've thought about like using other halogens besides fluorine in those positions just to see what the effects would be.
Yeah, so we haven't used any other halogens besides the fluoro group that I know of. If other schools have, I think what they have. So like we're just, I guess, based on, I don't know their results, I would be interested in looking at that. But the form of the drug, the dipeptide, is kind of like a baseline, and other schools are kind of like testing, I guess, like if there's another halogen or another amino acid, and like we're doing our own. So when we collaborate, like we have like a baseline model, but we're changing it based on what like we're adding to it, and the other schools are changing it themselves, so we can have one big collaboration, and so we don't have to do all the trials ourselves.
I have a question from Dr. Holbrook for you. Would you be able or interested to test a different administration or exposure technique, such as aerosolized antibiotics?
I think that'd be an interesting thing, I guess, because I mean, if it's a bacterial infection in your lungs, like to be able to inhale it rather than just consume it by swallowing it. So I think that would be interesting. Once we kind of, I guess, figure out which pairs work the best, the way that we're doing right now, that could be a next step, doing aerosol medicines.
And to add on what Hannah said, in an aerosol form of a treatment, the molecules of the drug itself are smaller, so it would allow for better access to the lungs. So if we found a type of medication that would work, doing it in the laboratory, testing it that way, we could then further test it by putting it in aerosol form, which I believe would make it more efficient if we have the correct dipeptide strain.
Are there any other questions?
I have one real quick.
Go for it,
Of course you do.
So we learned in biochem, and for people who haven't had it, that the human body can only process L forms of amino acids. So your research showed that the D forms were actually a little bit more successful. How do you think that's viable in a human study if it went further, or do you think it's more manageable that if we can't break it down, then therefore it would help the bacteria be killed faster?
Yeah. Well, all the amino acids in our body that we make are L amino acids, but a lot of other like prominent antibiotics are D forms. So like, I guess in our particular test, the D forms are more effective. I'm not sure what other antibiotics are D forms, but I've read that a lot of times when we talked about in biochem, they are the D forms. which has to do with, I don't know exactly the reason, but just the way the antibiotic interacts with the bacteria.
And from research that I've looked up, it also has to do with, because the body is more focused and can synthesize the L form better, the D form can be more resistant and more focused on the bacteria itself, rather than more of the antibiotic working on the bacteria than the body working on the antibiotic.
Yeah.
Any other questions? All right, before you all run away, I want to say thank you so very much for being a part of tonight's session. I know this is not a normal class time. I know this is very abnormal for all of us. So thank you so much for being a part of this. The Rise Above Committee says thank you. Dr. Giesey and I say thank you to all of you for being a part of this session. And I know I speak for all of the faculty and the administration and the staff when we say that we really, really hope that we can see you in person in the fall. Because personally, I am done with this online stuff. I cannot wait to see you all. If you are graduating this year, congratulations. We are so proud of you, and we cannot wait to see what you do next as a Milligan graduate. Thank you guys for being here tonight, and we will see you all soon. Goodbye.